The laws of logarithms. For the following laws, x is greater than 0, y is greater than 0, a is greater than 0, a is not equal to 1, and r is any real number. All of these laws follow directly or indirectly from the laws of exponents, and from the properties of inverses, since logarithmic functions are the inverses of exponential functions. Law number 1. The log base a of 1 is equal to 0 if and only if a to the 0 is equal to 1. Law number 2. The log base a of a is equal to 1 if and only if a to the first is equal to a. Law number 3. A raised to the power of the log base a of x is equal to x. This law follows directly from the property of inverse functions that states the composition of a one-to-one function and its inverse is equal to x, or the independent variable. Let f of x equal the exponential function a to the x, then its inverse is the log base a of x. Forming the composition, which must equal x, in this order, f composed with f inverse of x, means that we will input the logarithmic function into the exponential function. That is, form the composition f of the log base a of x. In doing so, we get a to the power log base a of x. Law number 4. The log base a of a to the r power is equal to r. This law also follows directly from the composition of inverse functions. We will let f of x equal a to the x again, and f inverse of x equal the log base a of x. We will form the composition in the opposite order this time. X equals f inverse of f of x, which means we will input the exponential function a to the x into the log base a of x. In doing so, we achieve the log base a of a to the x power. Substituting r for x, it is proven. Law number 5. The log base a of x plus the log base a of y is equal to the log base a of the product x, y. Let the log base a of x equal m. Likewise, let the log base a of y equal n. If the log base a of x is equal to m, then a to the mth power is equal to x. Similarly, if the log base a of y is equal to n, then a to the nth power is equal to y. Therefore, the log base a of x times y is equal to the log base a of a to the mth power times a to the nth power, substituting, which is equal to the log base a of a to the m plus n, a property of exponents. This is equal to m plus n by law number 3. Substituting for m and n, we get this is equal to the log base a of x plus the log base a of y. Law number 6. the log base a of x minus the log base a of y is equal to the log base a of the quotient x over y. The proof for this law is similar to that for law number 5. Law number 7. The log base a of x to the r equals r times the log base a of x. Expanding x to the r by the definition of an exponent, we get the log base a of x to the r equals the log base a of x times x times x, r factors of x. This is equal to the log base a of x plus the log base a of x plus etc. until we get our number of terms in the sum. This is law number 5 again. And then this sum of our terms is equal to r times the log base a of x. This is the definition of multiplication. Law number 8. If x equals y, then the log base a of x equals the log base a of y. This follows logically from law number 3 and from the exponential property that states if a to the x is equal to a to the y, then x must equal y. Law 3 states that a raised to the power log base a of x is equal to x. It follows that a to the log base a of y is equal to y. So if x equals y, it follows that a to the log base a of x equals a to the log base a of y by substitution. Applying the exponential property, this implies that the log base a of x is equal to the log base a of y. Law number 9. If the log base a of x is equal to the log base a of y, then x is equal to y. The proof for this law is very similar.